Okay, so next would be the multi-core programming. Okay, so for application programmers, there are 5 areas where a multi-core chips present new challenges. Okay, so these are identifying the tasks, okay, balance, you've got data splitting, data dependency, testing, and debugging. So let's start with dividing activities or identifying tasks. So this means examining application to find activities that can be performed concurrently. Okay? When you say balance, finding tasks to run concurrently that provide equal value. Example, don't waste a thread on a trivial tasks. All right? So next would be data splitting. So to prevent the threads from interfering with one another, so we have to perform data splitting. Next is data dependency. Okay? So when you say data dependency, if one task is dependent upon the result of another, then the task need to be synchronized to assure access in proper order. Okay? And last would be testing and debugging. So inherently more difficult in parallel processing situation, as the race conditions that we mentioned on the processes become much more complex and difficult to identify. Okay? Now, in a multi-core programming, so we will be encountering terms of parallelism and concurrency. Okay? Now, what's the difference between these two? So by definition, when you say parallelism, it implies a system can perform more than one task simultaneously. Okay? Whereas concurrency supports more than one task making progress. So single processor, you've got the core, dual core, multi-core, octa-core, okay? You've got the scheduler providing concurrency. All right? Okay, so we've mentioned earlier concurrency and parallelism. Okay, so a recent trend in computer architecture is to produce chips with multiple cores. Okay, you've got dual cores, quad core, you've got octa core. All right, so a multi-threaded application running on a traditional single core chip would have to be interleave the threads. Okay, so as shown here. So this is a concurrent execution on a single core system. Okay, now on a multi-core chip, however, the threads could be spread across available cores. So this is an example of a dual core here. Okay, and the threads are spread across this available cores here. So T1 or thread 1, thread 2, thread 3, and thread 4, and so on. So they are distributed among the available cores. Okay, so allowing through parallel processing. Okay, so for operating systems, multi-core chips require new scheduling algorithms. So to make better use of the multiple cores available. So as multi-threading becomes more pervasive and more important, so thousands instead of tens of threads, okay, CPUs have been developed to support more simultaneous threads per core in hardware. So that means with multi-core, okay, so the performance is of course faster than a single core. Okay, if we have a single core and a dual core, okay, so compared, so of course you've got several tasks distributed on a single CPU, whereas in here the threads are distributed on multiple cores. Okay, so that's faster, of course. All right, so next would be the types of parallelism. So in theory, there are two different ways to parallelize the workload. Okay, so these are the data parallelism and the task parallelism. Okay, so when you say data parallelism, so this divides the group up amongst multiple cores or threads and performs the same task for each subset of the data. So for example, dividing a large image into pieces and performing the same digital image processing on each piece on a different core. All right, so that is data parallelism. Now, when you say task parallelism, so dividing the task to be performed among different cores and perform them simultaneously. So in practice, no program is ever divided up solely by one or other of this, but instead some sort of hybrid combination. Okay? Okay, so next would be showing the data and task parallelism. So what's the difference between these two? As mentioned earlier, when you say data parallelism, so distribute subsets of the same data across multiple cores, same operations on it. All right. So when you say task parallelism, distributing threads across cores, okay, each thread performing a unique operation. All right. Okay. So next would be the Amdahls Law. Okay. So what is this Amdahls Law? So it identifies performance gains from adding additional cores to an application that has both serial and parallel components. So S is for serial portion and N is the number or the processing cores here. So this would compute this, or this would improve or speed up, okay, the performance. That is if application is 75% parallel and 25% serial. So moving from 1 to 2 cores results in a speed up of 1.6 times. Actually, it's not doubled, all right? So it's not that if we are using a single core, okay, and we are using a dual core on the other end, so we cannot conclude that the process has been doubled, okay? So to compute that speed up, you'll have this formula here, okay? So, and as mentioned here, no, if the application is 75% parallel and 25% serial, so moving from a single core to a dual core results to the speed of 1.6 times only. All right. So as n approaches infinity, so speed up approaches is 1 over s here. Okay. Now the serial portion of the application has this proportionate effect on the performance gained by adding additional cores. Okay. So this is what is stated on the Amdahls Law presented in the previous slide. Okay, so if you'll have here, this on this x-axis, you've got the number of processing cores, and on the y-axis, you've got the speed up. So if you are using a dual core, so it's something like 1.6, right, based on the computation. Okay, so if you are using a quad core, of course, it's less than times 4, okay? All right, so next would be the user and the kernel threads, okay? So there are two types of threads to be managed in a modern system, and these are, of course, the user threads and the kernel threads, all right? So when I say user threads, management done by user level, okay? And kernel threads is supported by the kernel, okay? So for the user threads, so this includes the POSIX threads, okay, which are used in Linux, okay. You also have this Windows threads on Windows, of course, and Java threads. Now for the kernel threads, so virtually all general purpose operating system, including Windows, Linux, Mac OS, iOS, and Android, these are all under kernel threads. All right. Okay. So user threads are supported above the kernel. Okay. So this is our kernel threads. This is our user threads. So user threads are supported above the kernel without kernel support. Okay. So these are threads that the application programmers would put into their programs. And when you say kernel threads are supported within the kernel of the OS itself. So all modern OSs support kernel level threads, allowing the kernel to perform multiple simultaneous tasks and or to service multiple kernel system calls simultaneously. Okay. Now in a specific implementation, the user thread must be mapped to kernel threads. So using one of the following strategies here. Okay. So there are 3 multi-threading models, and that includes many-to-one, one-to-one, and many-to-many. Okay, so what's the difference between these three here? Okay, so let's start with many-to-one. Okay, so in the many-to-one model, many user-level threads, all right, are mapped into a single kernel thread here. Okay, so thread management is handled by the thread library in the user space. Okay, which is very efficient. So however, if a blocking system call is made, then the entire process blocks even if the other user threads would otherwise be able to continue. Okay, so one thread blocking causes all to block. Now, because a single thread or a single kernel thread can operate only on a single CPU, the many-to-one model does not allow individual processes to be split across multiple CPUs. Okay, so green threads for Solaris, okay, and GNU portable threads implemented the many-to-one model in the past, but few systems continue to do so today. All right, so the next one would be one-to-one. Okay, now with one-to-one model, it creates a separate kernel thread to handle each user thread here. So there is a corresponding user threads, okay, so for every kernel threads here and vice versa. Okay, so one-to-one model overcomes the problems listed above involving blocking system calls and splitting of processes across multiple CPUs. So however, the overhead of managing one-to-one model is more significant, involving the overhead and okay, the slowing down of the system. So most implementations of this model place a limit on how many threads are created. Okay, so these are being implemented on Windows and Linux. Okay, so next would be the many-to-many model. With many-to-many model, it multiplexes any number of user threads onto an equal or smaller number of kernel threads. So combining the best feature of one-to-one and many-to-one models. So users have no restrictions on the number of threads created. Okay, so blocking kernel system calls do not block the entire process. So process can be split into or across multiple processors if you're using multiple processors, and individual processes may be allocated variable numbers of kernel threads depending on the number of CPUs present and other factors. All right. Okay, so how about this two-level? Okay, how about this two-level model? So what is this? So the two-level model is a popular variation of the many-to-many model. Okay, so which allows either many-to-many or one-to-one operation. Okay, now this model is being implemented on IRIX, HPUX, and the True64 Unix. Okay, as did with Solaris prior to Solaris 9.